today's video, we're going to be talking about equivalence relations and the closely related notion of partitions of sets. Now, there might be a chance that you're already quite familiar with equivalence relations. These come up, say, when you're taking the quotient of a group by a normal subgroup, or perhaps you're taking the quotient of some topological space by, well, an equivalence relation, or say the integers modulo n. But for us, it's going to be worthwhile to make these notions precise, although some of these ideas have probably been proven in earlier courses. I do think it's worth getting a grip on these from the ground up, and there's even going to be some connection to the axiom of choice, which we're going to talk about later on. So let's get to work defining what an equivalence relation is. What it is a special type of binary relation. So an equivalence relation is a binary relation. So I should say an equivalence relation E, let's give it a name, is a binary relation on a set A. What this means is that the binary relation E is a subset of A cross A. So the domain and range both belong to A themselves. There's just one set being related to itself in this case. And it's going to satisfy three conditions on top of this. So the first condition is that it is reflexive. The second is that it is symmetric. And the third relation is that this we require it to be transitive. So what all of these mean, for the first case, reflexive says that for all elements little a in our big set A, we have that A is related to itself under E. Symmetric says that for any two elements belonging to A, if it is the case that A is related to B, then B in turn must be related to A. And finally, transitivity says that if we have three elements, A, B, and C, all belonging to A, then if it's the case that A is related to B and B is related to C, then it must also be true that A is related to C. So this is the definition of an equivalence relation. We see that if I had some element and it was related to a second element B, by symmetry I can get back to that original element. And the same goes if there's any sort of chain going to different elements using things like transitivity and things like symmetry. I should always be able to get back to the element I started with following out some chain of relations. So what I'm trying to say here is that we should view elements which are all related to each other as somehow clustered or grouped together. So that brings us to the definition of an equivalence class. So an equivalence class, this is a set which is defined to be all those elements in A such that X is related to A through our equivalence relation E. Now notice this is this definition would be the same if we said A related to X because of the symmetry condition on equivalence relations. We establish a lemma now. So this says that if we have two elements A and B belonging to our relation A, then two things happen. The first is that A is going to be related to B if and only if the equivalence classes of A and B are equal as sets. And the second condition says that A is not related to B. This means the same thing as that the pair AB does not belong to E, if and only if the intersection of these equivalence classes is empty. We give a proof of this theorem now. So we'll, of course, start with the first part of the theorem, and we'll start with the first implication. So suppose it were the case that A and B are two elements of A which are related through E. in order to show that the equivalence class of A is equal to the equivalence class of B, we have to show that all the elements of A belong to B, the equivalence class of B, and all the elements of the equivalence class of B belong to the equivalence class of A. Now, really, we only have to do half the work because A and B here are totally interchangeable, and we'll see the exact same argument carries through just by swapping the roles of A and B. So suppose that A was related to B, and let's assume that X belonged to the equivalence class of A. Well, by our definition of equivalence class, this means that X is in fact related to A. But since X is related to A and A is related to B, by the transitivity of an equivalence relation, we can conclude that X is in fact related to B, and therefore X is in the equivalence class of B. And this is exactly what we needed to show. As I mentioned, showing that the equivalence class of B is contained in A is almost identical to this exact process here. So let's consider the converse direction. Let's suppose now that the equivalence class of A were equal to the equivalence class of B. Well, we know certainly that by the reflexive property, A is related to A, and therefore it must be the case that A is in the equivalence class of A, and I should say this holds for any A belonging to our set capital A. And since we're assuming that this is in the equivalence class of A, well, this is being assumed to be equal to the equivalence class of B. In other words, we know that A must be related to B, again by the definition of equivalence class. And that concludes the converse of that direction. In order to prove the second part of this lemma, we're going to proceed by a proof by contradiction. So we suppose it's the case that A is not related to B, and we assume towards a contradiction that the intersection is not empty. That is, we can find some X which lies in both equivalence classes. Well, since X is in both equivalence classes, this means that X is related to A, and that X is related to B. But by symmetry, we also get that A is related to X. And now we can combine A related to X and X related to B, again using the transitivity property, to obtain that A must be related to B, which is a contradiction. So therefore, if A is not related to B, it has to be the case that the intersection is empty. Now the converse direction will also prove by contradiction. So suppose it were the case that the equivalence class of A intersected with the equivalence class of B was in fact empty, and contrarily we'll assume that A is actually related to B. Now the problem is, of course, is that since A is related to B, this means that A belongs to the equivalence class of B. And we certainly know that since A is related to A, by definition, it must also belong to the equivalence class of A. And here we already see our contradiction, because we've now found an element which lies in both equivalence classes, and therefore it lies in their intersection, which we've assumed to be empty. Now we come to the second main concept of this video, and that is the definition of a partition. So we say that a system of sets S is a partition of a set A if two things hold. That is, if we have elements X and Y of S, if it is the case that X is not equal to Y, then the intersection of X and Y is empty. And secondly, we require that the union of the set S be equal to A. What this is saying in terms of if we had, say, a picture of a set, we can imagine a partition as dividing up the elements of the set. So we can see that any of these regions which are separate from each other are disjoint, and once we put all the regions together, we get the entirety of this set, the entirety of everything within the black boundary. Now, in the case that we have some set A, and we have an equivalence relation on A, we form what's called the quotient set, which we sometimes simply say A modulo E, the equivalence relation E, again as a reflection of the integers mod n. This is going to be the set whose elements are equivalence classes of the relation for all elements belonging to the set A. And this leads us to the first of a couple theorems that connect the notion of partition to the notion of equivalence relation. And our theorem is that the set A modulo E is in fact a partition of the set A. Now the first part of the proof actually comes from the previous lemma. That is, if we were to suppose that we have two elements of A modulo E, well, these simply look like equivalence classes. So these are A, an equivalence class of some element A, and some equivalence class of some element B, which are not equal to each other. And if we look at condition 1, or rather we take the negation of condition 1, we can see that this tells us that A is not related to B. And then by the second condition, if A is not related to B, then it must be the case that the intersection of these two sets is empty, which is the first thing that we require of a partition. For the second part of a partition, let's suppose we had some element X, and that was in the union of our set A modulo E. Well, this means that the element X must belong to some set big X, which itself is a member of A modulo E. But A modulo E is the set of equivalence classes of A, so therefore the set X must be equal to some equivalence class of some element belonging to the set A. Since X belongs to this element, that means that X must be related to A. But the relation E is only defined on the set A, and therefore X must belong to A. So certainly we have that the union of A modulo E is contained in the set A. And secondly, if we had some arbitrary element A, little a of the set A, well, we know that it belongs to its equivalence class, and that equivalence class must belong to A modulo E. And now this is simply the definition of the union of a set. We've found a set which contains A and is an element of A modulo E. Therefore, A must be an element of the union of A modulo E. And thus we've shown that both conditions of a partition is satisfied by the set A modulo E.
We know now that if we have an equivalence relation, if we take the set A mod E, that will give us a partition of A. And there's actually a way to go in the opposite direction of this construction. To explain what I mean, given a partition S of a set A, we're going to make the definition E sub S, which is going to be the set of all ordered pairs of the Cartesian product of A with itself, such that there exists some set X belonging to S, where A and B both belong to X. The reason for this definition is the following lemma, is that E sub S is an equivalence relation. And we can see the first part of this, the fact that it's a binary relation, we can see already because it's a subset of A cross A. In order to verify that it is an equivalence relation, we need to check reflexivity, symmetry, and we'll need to check transitivity. So to prove reflexivity, suppose we had some A sitting in our set A. Well, we've decreed S to be a partition of A. So we know that big A is equal to the union of S. But since little a is in the union of S, that means that there exists some set X such that A is in X and X is in the set S. Well, A is in such a set, and so is A, yet again. So certainly A is E sub S related to A. As for symmetry, we can suppose we have two elements, A and B, belonging to our set A, such that A is E sub S related to B. Well, this simply means, by the definition of E sub S, that there is some set X, so that A and B both belong to X, and X belongs to S. Well, if A and B belong to X, then certainly B and A belong to X. We're not really saying much anything different, but this just tells us that B is also S related to A. And thus we have symmetry. Finally, for transitivity, we suppose that we have elements A, B, and C, so that A is ES related to B, and B is ES related to C. Well, this just means that there exists a set X, such that A and B belong to X, and X belongs to S, and a set Y, such that B and C belong to this set Y, and Y belongs to S. But this tells us that B is in the intersection of X and Y. And from the definition of a partition of a set, we saw that two elements of the partition, if they're not equal, then the set must be empty. Taking the converse of this, if the intersection is non-empty, that means the sets must have been equal to begin with. Therefore, we know that X equals Y. In other words, we know that A and C both belong to the same set X belonging to S, which by definition is that A is S related to C. This brings us now to the ultimate theorem of this video, and it's a two-parter, which says that first, given an equivalence E on a set A, given a relation E on A, we know that A mod E is a partition of A, and so using the construction of this relation E sub S, we can form the relation E sub A mod E, and this will be equal to the original relation E. And the second part of the theorem states that if we have S being a partition of A, then it must be the case that E modulo the equivalence relation coming from that partition must give us back the partition S itself. To prove statement A, let us first suppose that we had some ordered pair AB which belonged to the equivalence relation A sub A mod E. Well, what this means precisely is that, well, A is E A sub A mod E related to B. That is to say that A and B both belong to some matrix S, and that matrix belongs to the partition A mod E. But from our definition of A mod E, we know it's simply made out of equivalence classes. Therefore, our set X, hence A is related through E to X, B is related through E to X, which by the symmetry property tells us that X is related through E to B, and then combining A related to X and X related to B using transitivity, we have that A is related to B. Another way of saying this, of course, is that the ordered pair AB belongs to E. So we've shown that E sub A mod E is a subset of E. To prove the converse direction, we now assume that we have some ordered pair A and B belonging to the set E. Well, this means that A is related to B, in particular, that B belongs to the equivalence class of A under E, and, well, we know that A itself must belong to this equivalence class. Furthermore, the set A mod E is made out of such equivalence classes. Therefore, A and B both belong to some set which is in the partition A mod E. So, by definition of E sub A mod E, A is related to B. To prove part B, we let S be a partition of A. And let us suppose that we have some set X belonging to the partition A mod E sub S. Our goal is to show that this belongs to S itself. Well, again, A mod E is a set of equivalence classes. So big X here must be equal to the equivalence class of some little s under the equivalence relation E sub S. This is equal, by definition, to the set of all little a in A, such that A is related through E to S, such that A is related through E sub S to X. But this set, in turn, is those little a in A, such that there exists some set Y, so that A and X both belong to Y, and Y belongs to F. However, we know that little x, well, it's certainly in the equivalence class of under E sub S. And we said that this was equal to the set X. But we know now that whatever the set Y is, it belongs to the partition of S. Recall that if we have two sets belonging to a partition, if they're not equal, then they are disjoint. That is, if the intersection of two sets is non-empty, then the sets must be equal. Therefore, given all these A that share the set Y with X, must all be sharing the same set Y. That is, there is some unique Y such that A and X both belong to S. In other words, this set is the set of all A, little a in A, such that AX belong to Y for some fixed set Y, where Y itself is a member of the partition of S. Now, my claim is that this set is the set Y itself.
Suppose we had an element of the set on the left. That means that it belongs to A, and it satisfies the defining property of that set, which tells us precisely that it belongs to Y. So we have one of the inclusions right away. Alternatively, if we had some element that belonged to y, well, we know from this defining feature of the set on the left that y does belong to the set S. And since S is a partition of A, that means the elements of y must be elements of A. So certainly anything in y is in A, and of course it satisfies the condition that it belongs to y, so anything in y must belong to the set on the left as well. Now, if we trace back through this chain of equalities that we've shown, we've started with some set x, which is in A modulo E sub s, and we found out that it was equal to a set y, which belonged to S. And this is exactly one direction of containment that we wanted to show. So alternatively, we suppose that we start with some set x belonging to our partition S. And we note that this is equal to the set of all A in A, such that A is in X and X is in S. This is essentially the argument that we showed. Now, if we were to choose any little x inside big X, then we could simply write this set as the set of all A, such that A is related through E sub s to X. But this is simply the equivalence class of X under the relation E sub s, and we know that this must be in the set A modulo E sub s by definition. That is to say, our set large X must belong to E modulo E sub s. And so we have containment in both directions, thus finishing our theorem. Consider again our drawing of a partition of a set. We see that for each of the partitions here, we can pick one element to represent that entire part of the partition. All the elements in a given set of the partition are related to each other under the relation E sub s. And when two elements are related, we know that their equivalence classes are the same. So we might hope to pick some set of elements, one from each part of the partition to represent that partition. As a quote-unquote real-world example, let's consider the integers modulo n. Now, really, the elements of this thing are equivalence classes. That is, it's an equivalence class of integers m under a relation E, where m is related to x if and only if m is congruent to x modulo n. And so really this is an equivalence class of infinitely many numbers, but what we do is we choose a representative for each of these class that lies between 0 and n minus 1. So this is an example of where it's useful to choose representatives. To be more formal about what I'm saying, I'm going to make the following definition, and that is a set X, which is a subset of some set A, is said to be a set of representatives for, and here by the equivalence of our previous theorem, we can either say that it's a set of representatives for a partition S, or we can say that it's a set of representatives for the corresponding relation, since these are now interchangeable. If for all sets Y which belong to the partition, X intersect Y is always just a singleton set. That is, it's just a set with one element, whatever that element may be, being some element of A. And so the question is, well, can we always do this? Is the set of representatives always a well-defined notion? Now, it seems up above from this picture that I've drawn, seems quite intuitively obvious. Yeah, I can pick an element from each of the sets of the partition, it really shouldn't matter. It seems like a very easy thing to do. They're all non-empty sets. Just take an element from each of them. And certainly, it's a very reasonable thing. We see that we can do this when we're talking about the integers modulo n. Interestingly, though, this is actually a question which is independent of the Zermelo-Frankel axioms. And we haven't even covered all of these axioms yet, but they're independent of the sort of standard original set theory, if you will. And the thing that I'm getting at here is that this result actually depends on the famous axiom of choice. So we're still a few sections away from talking about the axiom of choice and its consequences, but already, even in these early stages, we can see some of the impact that it's having on the theory. That's going to do it for this video. Like always, if you have questions, comments, concerns, please leave them in the comment section below, and I'll catch you in the next one.